Hello students, so welcome back to my video lecture 2 on S block elements. Hope you remember what we have learnt in video lecture 1. So in video lecture 1 we understood what are S block elements, what are alkali metals, alkaline earth metals. We also understood their electronic configuration. So what was the general outer electronic configuration of alkali metals? It is inert gas core NS1, and alkaline earth metals, okay, inert gas core NS2, isn't it? And I've told you in the previous video that, okay, in this video lecture 2 I'll be talking about these physical properties. Which are those? Atomic radius, ionic radius, valency, ionization enthalpy, metallic character, melting point and boiling point, density and color to the flame. So let us discuss all these properties in detail one by one. Okay students, so I'll be starting with the first physical property. What is it? Atomic radius. Okay, yes. So we have studied about the variation of atomic radius along the period and down the group, isn't it? Variation of atomic radius along the period and down the group, isn't it? Okay, so first physical property, what is it? Atomic, okay, radius. Atomic radius. Okay, yes. So how does atomic radius vary along the period and down the group? So we know this very well. Along the period, okay, along the period, atomic radius, yes, keeps on decreasing, isn't it? As we go from left to right in the periodic table, from group 1 to group 18, from group 1 to group 18, sorry, or else if you can consider group 1 to group 17, the atomic radius decreases steadily from one group to another group to another group, like that, isn't it? From 1 to 17 there is a gradual decrease in atomic radius, isn't it? So along the period atomic radius decreases, correct? Okay, yes. Down the group, atomic radius increases, okay, isn't it? Atomic radius increases. Say yes. Yeah, correct. Okay, so as we move from top to bottom in the periodic table, from top to bottom there is an increase in atomic radius. Hope you know why atomic radius increases along the decreases along the period and increases down the group. So we have already learnt it in periodic table, so let us not waste our time discussing the same thing here also. Okay, so now I'm going to consider alkali metals and alkaline earth metals. Come on guys, list out alkali metals. So lithium, okay, sodium, potassium, rubidium and cesium. Let us restrict our discussion only up to cesium. Okay, next in alkaline earth metals we have beryllium, magnesium, okay, calcium, strontium and barium. Here also we will restrict it only up to barium because francium and radium are radioactive in nature. So what happens when I move from lithium to cesium down the group? From lithium to cesium, you know, down the group, okay, atomic radius increases. Is that correct? So if I talk about alkali metals, look at the, okay, variation of atomic radius. Okay, so lithium, okay, is smaller than sodium, sodium is smaller than potassium, okay, potassium is smaller than rubidium, rubidium is smaller than cesium. Okay, so now I can say cesium is going to be the big element among the alkali metals and lithium will be the small element among the alkali metals. Okay, so there is a increase in atomic radius down the group from lithium to cesium, no doubt in it. Okay, and on the same lines if I talk about alkaline earth metals, okay, alkaline earth metals, okay, alkaline earth metals. So what happens when I go from okay, beryllium to barium? Okay, same thing, same phenomena. From beryllium to barium there is a gradual increase in atomic radius, isn't it? Okay, so beryllium, the size of beryllium is smaller than magnesium, okay, it is smaller than calcium, it is smaller than strontium, strontium is smaller than barium. There is no exception at all. Okay, there is no exception at all. There is an increase in atomic radius from beryllium to radium. So which is the big element among alkaline earth metals? It is, okay, barium. Which is the small element among the alkaline earth metals? It's going to be beryllium. Okay, please remember these orders. Okay, there is an increase in atomic radii down the group, there is an increase in atomic radii down the group. Okay, now if I compare these two elements, if I compare between alkali metals and alkaline earth metals, from alkali metals and alkaline earth metals, that means I'm going from left to right. Okay, I'm going from left to right. As I go from left to right, that means along the period atomic radius decreases. Therefore, can I say that alkaline earth metals are smaller than alkali metals? Isn't it? Okay, alkaline earth metals are smaller than alkali metals. So I'm going to conclude it here. Yes, let me write. Alkaline earth metals are smaller than alkali metals. Okay, alkaline earth metals are smaller than alkali metals. And you should note one more point, very important point, that okay, yes, each alkali metal is the biggest element in its own period. I hope you know this. Okay, in its own period. That means lithium, this is the second period element, isn't it? Second period element. This is third period. Okay, yes, this is fourth period. Yes, this is fifth period. Yes, this is going to be what? Sixth period, correct? Sixth period, isn't it? Okay, so lithium will be the biggest element when compared to all other elements of second group. Okay, so now, and sodium is going to be the biggest element of all other elements in the same third period, I'm sorry. Okay, potassium is going to be the biggest element in the fourth period. Okay, yes, rubidium will be the biggest element among all the elements of fifth period, like that. In the sixth period, okay, in the entire sixth period, which is the biggest element, it's going to be cesium. Okay, simple. Any doubts? Okay, so I hope you have understood about atomic radius. Please note these points, simple points. Okay, yes. Now if I talk about, okay, the next physical property, what is it? The next physical property, okay, the next physical property is going to be, okay, yes, we have finished atomic radius. The next I'll be talking about ionic radius. Okay, yes, what about ionic radius? Yes, we know ionic radius will follow the same trend. Ionic radius will follow the same trend as that of atomic radius. That means along the period ionic radius decreases, down the group ionic radius increases. Same trend, there is no change in it. Okay, but here we'll be talking about ions. Okay, yes, we know, yes, alkali metals will form unipositive ion, okay, whereas alkaline earth metals will form, okay, dipositive cation. Okay, these will form unipositive cation, these will form dipositive, okay, dipositive cation. Okay, monopositive cation, dipositive cation. So that means, okay, if you look at the ionic radius, lithium ion will be smaller than sodium ion. Sodium ion will be smaller than potassium ion. Potassium ion will be smaller than rubidium ion. Rubidium ion will be smaller than cesium ion, isn't it? Okay, next, beryllium ion, Be2 plus. Beryllium ion will be smaller than magnesium ion, okay, which is smaller than calcium ion, which is smaller than strontium ion, and which is smaller than what? Barium ion. As I said, alkaline earth metals will form dipositive, okay, ions, whereas alkali metals will form monopositive ions. So in their own group, okay, there is a gradual increase in ionic radii from lithium to cesium and from beryllium to barium. Okay, now think, okay guys, just remember one more thing. Okay, as the positive charge increases, we know this, we have studied this in periodic table also. Okay, yes, as the positive charge increases, as the positive charge increases, we know effective nuclear charge increases and size decreases, isn't it? Okay, size decreases. Say yes or no? As the positive charge increases, effective nuclear charge increases and size decreases. Here, okay, they carry +2 charge. Alkaline earth metals carry +2 charge, whereas alkali metals carry plus charge. Okay, as the positive charge increases, effective nuclear charge increases. Therefore, the size decreases. That means even in ionic form, alkaline earth metals are smaller than alkali metals, isn't it? Even in ionic form, alkaline earth metals are smaller than alkali metals, isn't it? Therefore, I can conclude even in ionic form, okay, alkaline earth metals, okay, are smaller than alkali metals, Clear? Okay, so this is all about what ionic radius. Hope you have enjoyed. Okay, hope you have learnt it. So can I go with the next physical property? What is the next physical property? Yes, the next physical property is valency. Okay, let me talk about valency now. Valency. Yes. Okay. Now, what is the valency of alkali metals? Okay. What is the valency of alkaline earth metals? What is the valency of alkali metals and what is the valency of alkaline earth metals? Okay. Yes. Come on, quick. What is the valency of alkali metals? See, if I take lithium or sodium for that matter, anything, sodium, okay, what is the atomic number of sodium? It is 11, correct? What is its electronic configuration? 1s2, 2s2, 2p6, 3s1, 2p6, 3s1. Okay, I told you, okay, in the very first video itself, I am going to relate each and every physical properties and each and every chemical properties to the respective electronic configuration. Correct? So that is what I am telling you. Every time I have to keep writing what electronic configuration, if I have to tell you, if I have to make you understand the physical properties and the chemical properties. Now, what is the valency of sodium? What is the valency? So look here, sodium, okay, sodium, now if I consider the outermost electronic configuration, okay, if I consider the outermost shell, it has 1 electron in its outermost shell. That means it has to require, on a shorter note, it has to require 7 electrons to complete its octet structure. Is there somebody who can give 7 electrons to sodium so that sodium complete its octet structure in the outermost shell? No, nobody will give 7 electrons to sodium so that it can complete its octet. Therefore, what does sodium is going to do? Sodium, instead of waiting for 7 electrons, instead of waiting for somebody to give 7 electrons, okay, what it will do is, it will lose its 1 electron. It will lose its outermost electron. It is going to lose its outermost electron. When it loses its outermost electron, look here, it will attain neon gas configuration, isn't it? Okay. Upon losing its outermost electron, it is going to attain noble gas configuration. Therefore, okay, now same thing happens with all alkali metals. All the alkali metals, instead of waiting for somebody to give the electrons, they itself lose their outermost electron. What was the general outer electronic configuration of alkali metals? The general outer electronic configuration of alkali metal was inert gas core NS1, isn't it? Okay, alkali metals, it is NS1. Now, upon losing this 1 electron, all alkali metals will get inert gas configuration. Inert gas configuration. Therefore, I can say all alkali metals, okay, are monovalent. Monovalent, isn't it? Okay, monovalent, correct? Okay, yes or no? All alkali metals are monovalent. So if somebody will ask you what is the valency of alkali metals, what is that you're going to tell? The valency of alkali metals is 1. Okay, will they lose 1 electron or will they gain electron? They're going to lose 1 electron. Therefore, upon losing 1 electron, they will attain the nearest noble gas configuration. Okay, yes. So alkali metals are monovalent. What about alkaline earth metals? Consider the electronic configuration of magnesium. Okay, yes. What is the atomic number of magnesium? It is 12. What is its electronic configuration? It is 1s2, 2s2, 2p6, 3s2, 2s2, 2p6, 3s2, isn't it? Okay, just observe the outermost shell of magnesium. The outermost shell of magnesium has 2 electrons. That means it, in a shorter note I can say it requires 6 more electrons to complete its octet structure in the outermost shell. Is there anybody who can give 6 electrons? No, nobody will easily give those 6 electrons, okay, for magnesium to complete its octet. Therefore, what is magnesium going to do? Magnesium, instead of waiting for somebody to give or to donate 6 electrons, it itself loses its outermost 2 electrons. It will lose its outermost 2 electrons. Okay, when it loses its outermost 2 electrons, okay, it will acquire neon gas configuration. Is it correct? It is going to acquire neon gas configuration. Neon gas configuration, it is going to become stable. Okay, hence that is the same, that is the truth. This is the same phenomena is true with all alkaline earth metals. What was the general outer electronic configuration of alkaline earth metals? It was inert gas core Ns2, isn't it? Okay, all alkaline earth metals, okay, they will lose the 2 electrons, okay, in the outermost shell, and when they lose the 2 electrons of the outermost shell, they're going to attain the nearest noble gas configuration. Hence I can say alkaline, okay, how many electrons are they ready to lose? They're ready to lose 2 electrons. Therefore I can say alkaline earth metals are divalent, correct? Alkaline earth metals are divalent. Okay, so what is the valency of alkali metals? 1. What is the valency of alkaline earth metals? 2. Okay, simple. So all alkali metals, okay, they are ready, they will lose 1 electron and they will attain the nearest noble gas configuration, inert gas configuration. All alkaline earth metals, they will lose 2 electrons and they acquire the nearest inert gas configuration. Therefore alkali metals are monovalent, okay, alkaline earth metals are divalent. Okay, hope you got it. Yes, no doubts in it. Next, let us talk about the next physical property. What is it? I'm sorry, each time I'm rubbing this elements. So this is from 3rd period and this is from 2nd period. Is that correct? Okay. Well, what is the next physical property? The next physical property, the 4th one, is supposed to be its ionization enthalpy. Okay, ionization enthalpy. Are you getting my point? Yes. Now, by the way, what is ionization enthalpy? Yes. Okay, what is ionization enthalpy? Anybody please define what is ionization enthalpy? Yes, ionization enthalpy is the amount of energy, okay, amount of energy required to remove an outermost electron from an isolated gaseous ground state atom. Ionization enthalpy is defined as the amount of energy required to remove the outermost electron from an isolated gaseous ground state atom. Okay, it is called as what? Ionization enthalpy. Is that correct? Okay, yes, well and fine. Now, what about the ionization enthalpy of alkali metals and what about the ionization enthalpy of alkaline earth metals? Okay, how does ionization enthalpy vary along the period and down the group? Yeah, come on. We know ionization enthalpy, we know that ionization enthalpy is inversely proportional to size. Is that correct? Is inversely proportional to size. As the size increases, ionization enthalpy decreases. As the size decreases, ionization enthalpy increases. Is that correct? Okay. Ionization enthalpy is inversely proportional to size. Okay. That means the radius. Is it ionic radius or atomic radius? Anything is fine. Okay. How does ionization enthalpy vary along the period and down the group? Yes. Along the period, we know along the period size decreases, isn't it? Along the period from left to right, from group 1 to group 17 in the periodic table, if we go from left to right, the size, atomic radius, ionic radius decreases. As the size decreases, ionization enthalpy increases. So along the period, ionization enthalpy increases, whereas down the group, we know down the group, okay, down the group atomic radius increases, isn't it? Okay, atomic radius increases, ionic radius increases. As the size increases, ionization enthalpy decreases. Yes, okay, ionization enthalpy decreases, isn't it? Okay, ionization enthalpy decreases. Correct. Now, okay, if I talk about the ionization enthalpy of alkali metals, what happens to ionization enthalpy of alkali metals from lithium to cesium? So as we go down the group, down the group ionization enthalpy decreases. So what is the order of ionization enthalpy for alkali metals? Okay, yes, what is the ionization enthalpy for alkali metals? Okay, yes, so our ionization enthalpy decreases down the group. It decreases down the group. Okay, therefore I can say lithium has more ionization enthalpy than sodium. Sodium has more ionization enthalpy than potassium, than rubidium, than cesium. Cesium has least ionization enthalpy. Okay, among alkali metals, lithium has highest ionization enthalpy and cesium has least ionization enthalpy. Since cesium has least ionization enthalpy, it will easily release its electron, its outermost electron, isn't it? Okay, now if I talk about the ionization enthalpy of alkaline earth metals, okay, alkaline earth metals, okay, so what happens to ionization enthalpy from beryllium to barium? Okay, yes, again same thing, decreases from beryllium to barium. Therefore what is the order of ionization enthalpy? Beryllium has more ionization enthalpy than magnesium. Magnesium has more ionization enthalpy than calcium, then strontium, then barium. So barium has least ionization enthalpy. Therefore it is easy to remove, okay, it is very easy to remove the outermost electron from barium when compared to beryllium. Okay, yes, clear? So now as we move from left to right, okay, that means from alkali metal to, okay, alkali metal groups to alkaline earth metals, along the period, okay, what happens to ionization enthalpy along the period? Increases, isn't it? So that means as we go from alkali metal group to alkaline earth metal group, ionization enthalpy will increase, okay. So therefore I can say the ionization enthalpy of alkaline earth metals is more than the ionization enthalpy of alkali metals. Simple? Yes. Okay, note this point, alkaline earth metals, okay, yes, has more ionization enthalpy than alkali metals, okay, than alkali metals. Okay, any doubts with this? Okay, yes, well, okay, this doesn't complete ionization enthalpy. I am going to write a very important statement. Okay, please note that statement. What is that statement? Okay, I am going to make a remarkable statement now, okay, regarding alkali metals, regarding the ionization enthalpy of alkali metals. Okay, so regarding, okay, and before that, before I make that statement, so note this point, among all the elements in the periodic table, among all the elements, okay, in the periodic table, okay, yes, alkali metals, okay, have least ionization enthalpy, isn't it? Have least okay, ionization, okay, enthalpy, okay, they have least ionization enthalpy. Understood? Okay, among all the elements in the periodic table, alkali metals have least ionization enthalpy. So after this, a very important statement. Okay, please note this. As I said, it's a remarkable statement. What is that? Okay, see this. The first ionization enthalpy, the first, okay, ionization enthalpy of alkali metals, okay, is low, okay, whereas, okay, the second ionization enthalpy, can I write IE for ionization enthalpy, please? Okay, please note that point. IE means ionization enthalpy, whereas the second ionization enthalpy of alkali metals, okay, is nearly 10 times the first ionization enthalpy, nearly 10 times the first ionization enthalpy. First ionization enthalpy, are you getting my point? First ionization enthalpy, okay, please note this. What am I telling you here? Okay, the second ionization enthalpy is nearly 10 times the first ionization enthalpy for alkali metals. That means the second ionization enthalpy is very high when compared to the first ionization enthalpy. We know first ionization enthalpy of alkali metals is very low, but the second ionization enthalpy is very high. Why the second ionization enthalpy is so much high? Why it is so much high? Okay, yes, again let us take up the electronic configuration. Look at for sodium. Yes, for sodium, okay, the first ionization enthalpy is about 452 kilojoules per mole, okay, whereas the second ionization enthalpy is about 4520 kilojoules per mole. Don't you think it is approximately 10 times more than the first ionization enthalpy, isn't it? 10 times more than first ionization enthalpy. Why the second ionization enthalpy is so high when compared to the first ionization enthalpy? Okay, yes, let us take up the electronic configuration of sodium. What is the electronic configuration of sodium? It is 11. Atomic number is 11. What is its electronic configuration? 1s2, 2s2, 2p6, 3s1. Now for first ionization enthalpy, okay, I'm going to remove the last outermost electron. Okay, I'm going to remove the first outermost electron. Look here, upon losing the outermost electron, okay, sodium is going to acquire the nearest noble gas configuration, isn't it? Okay, upon losing one electron, sodium is going to acquire the nearest noble gas configuration. We know, okay, no, inert gas configuration is a stable configuration. It is very difficult to remove the electrons from a stable configuration, or it is very difficult to add the electrons from the stable configuration. So therefore, okay, sodium upon losing one electron, it has gained noble gas configuration. Now it is already stable. It doesn't want to lose further more electrons. Hence, if at all if you want to remove the next electron, you have to supply very high energy. How much of energy? 4520 kilojoules, almost 10 times the first ionization enthalpy. Got it? Clear? Yes, that is what it means. The first ionization enthalpy of alkali metals is low, correct? Whereas the second ionization enthalpy of alkali metals is nearly 10 times the first ionization enthalpy. Okay, clear? Yes. Now let us move on to the next okay, physical property. Yes. Okay, what is it? Physical appearance. Okay, the next physical property that I am talking about here is physical appearance. Physical appearance. Okay, Now, if I talk about the physical appearance, observe here. See, alkali metals, okay, and alkaline earth metals, alkali metals and alkaline earth metals, alkaline earth metals, got it? Alkali metals and alkaline earth metals. See, alkali metals are, okay, silvery white metals, silvery white, okay, they'll have a bright appearance on their surface, okay, silvery white metals, okay. Alkaline earth metals are also silvery metals, okay, but they look dull when compared to alkali metals. They are not as bright as what alkali metals, okay. They are silvery earth metals, they are silvery, okay, compounds, they are silvery elements, but they are not as bright as what alkali metals, okay. Well, alkali metals are soft, they are so soft that they can be cut using a plastic knife itself, okay. They can be cut using a plastic knife itself. They are so soft, whereas alkaline earth metals are also soft, okay, but they are harder than alkali metals. 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 That means they cannot be cut using a simple plastic knife. They want a sharp edged tool for them to be cut. Got it? Clear? Yes. So that's what about their physical appearance. Nothing more in that. They are silvery white. Okay. They are also silvery metals. They are also silvery elements, but they are not as bright as what alkali metals. Okay. They are soft. They are also soft. They are so soft that they can be cut using a plastic knife. Okay, they are soft, but they are harder than alkali metals, okay. Is that simple? Yes. So guys, now we are left with okay, 3 more physical properties of alkali metals and alkaline earth metals. So I'm going to complete that in the next video. Thank you.